Alright, so in this video we're going to look at some nested quantifiers, see if we can really blow our minds with this topic. And so let's start with the example that's on the screen. I've got the statement P of xy, which represents the statement student X has taken class Y. And we have to have our domain. So domain on X is all students in my class, and the domain on Y is all computer science classes at MCC. And so we can look at different ways to quantify that statement with nested quantifiers. So maybe if we take a look at this first statement, we've got the existential quantifier on both X and Y. And so remember, the existential quantifier just means that we have to select one value from the domain. So the way that we might say this in English is, there exists a student in my class who has taken one computer science class at MCC. That would be a perfectly fine translation. Or you might say, some student in my class has taken some computer science class at MCC. That would also be fine. So I think that's pretty straightforward. If we move on to this next quantified statement, we've got the universal quantifier on X. So that allows for all values of X, and the existential quantifier on Y. So the way you might translate this is, all students in my class have taken some computer science class at MCC. Or equivalently, you could say, you're just being picky about the wording. If you change it, which is fine, you might word it a little bit differently, but you might say, every student in my class has taken at least one computer science class at MCC. Either of those translations would be perfectly fine. Slightly different, but correct nonetheless. And this third one, same idea, it's just that the X and the Y, the order's been reversed, so the way that we say this will be a little bit different, has a little different meaning. We've got the universal quantifier on Y, and the existential quantifier on X. So we allow for all values of Y. So we might say, all computer science classes at MCC have been taken by one student in my class, or something along those lines. Again, you might say something slightly different that would be perfectly fine. Right, so those types of problems are helpful just for, getting an idea of how the nested quantifiers work. But of course, we ultimately want to apply these ideas to more mathematical statements. So maybe we have something like this. Something like this, where we say that our domain consists of the integers, and so this means that both n and m are integers. And so, so n consists of all integers, m consists of all integers. And so, I suppose one thing you can start with is, can you even say the statement? Can you try to say the statement in words? So there exists an integer, so that when we square it, it's going to be less than all integers m. Does that seem to make any sense with what we know about the integers? Right, can I find the existence of some integer? So if I just pick an integer and square it, of course that would be 4. Is that going to be less than all integers m. Well, of course, 4 is less than some of the integers, but it's not less than all of the integers. I mean, it's less than 5, 6, and 7, but we can certainly think of some other integers that 4 is not less than. 3, 0, -3. Okay, so there seems to be some counterexamples that we could think of, and we only have to, right, in order to disprove a universally quantified statement, we only have to find one counterexample. And so this kind of goes back to that idea of if we have some number squared, it's always got to be positive, right? So what if we thought about a value for m that was not positive? We said something like this: pick m equal to -1. Then our statement, n squared less than -1, can't be true. N squared has to be positive, or possibly 0. So this statement is always, or let's say it this way, this statement is false for all integers n. Okay, so we found the existence, we found one m that makes this statement false for any value of n. Right, and so that shows that our statement must be false. Okay, so let's take a look at this statement. And again, we're using the same domain, the integers, and this looks similar. So let's see. For all integers n, does there exist some integer m where n squared is greater than or equal to m? So let's see. Can we think of some integer? Can we think of some integer that would work over here where when we use any other integer and square it, it would always be greater than or equal to this one? Well, now that maybe starts to make sense, because I mean, if you think about, in the last example we said, well, if we had 2 squared was 4, is there some other integer that's always greater than or equal to? Well, of course we can find a couple. I mean, 1 and 2 work. But what if we thought about negative integers, -10 or something like that? Right, when we square something, that's always going to be positive or 0. So it would always be greater than a negative integer. So this kind of starts to feel like maybe we pick some negative value for m, whatever negative value we want, and then if we look at our statement, that statement is true no matter what the value for n is, right? Because we take an integer and square it, n squared is always positive. So this statement is true for all integers n. And so this statement is true, and the reason I wanted to point this one out is because if I look at the relationship between this one and the last one, these two statements are the negation of each other. Right? If I negate there exists, I end up with for all. If I negate for all, I end up with there exists, and the negation of n squared less than m is n squared greater than or equal to m. So it makes sense that if we have one statement that's false, its negation should be true. So that's nice. Let's look at another one like this. Same domain, integers. So we have there exists n, so that for all m, n squared greater than m. Now this looks a lot like the last one that I did. Except notice in the last one this guy was for all and this guy was there exists. So the existential and universal quantifiers are switched. It's going to change the statement and possibly the truth value. Right? So does there exist some integer n so that when I square it, it's greater than all integers m? Now does that make any sense? If we go with, right, we squared 2 and that gave us 4. Right. Now remember in the last one we just had to find one that this guy was greater than. Now we're saying is, right, if we pick some integer and we square it, is that greater than all integers m? Well, no, it's not, because I mean we can think of some integers 5, 6, 100 that 4 is not greater than. Right? These guys are greater than 4. So it appears that this is false, right? So if we're going to prove this is false, we have to select some integer that we know is going to be greater than n squared. Right now we can't select a value. One mistake I see made a lot is we'll just say, well, let's pick n equals 2 and m equals 100. Well, then the statement has to be false because 2 squared is not greater than 100. Right, well that doesn't work because we can't just select a value, in this case we can't just select a value for n, right? Because if we're going to show this is false, we've got to show it's false for all values of n. We've got to show it's false for all values of n because we're trying to refute a existential statement. Now we do get to select a value for m, right? So, well, let's go with this. What if m is 100? I'm sorry. I'm going to back that up. That's not going to work either. Well, let's see what would happen. If I select m equals 100, then what would I have? I'd have n squared greater than 100. Okay, so I need something a little bit more in this one, right? Because I can't say this is false for all values of n. Right? I can't say this is false for all values of n. Right? Because what if n is 200 or something like that? Well, then the statement is true. Right? So I need to think a little deeper in this one. I'm going to have to pick a value for m that I know is greater than n squared. So let's pick m equals something that I know is greater than n squared. Say n squared plus 1. Right now, if I look at my statement, then I've got that. And if I subtract n squared from both sides, I end up with 0 greater than 1. And I'm going to have to cut this video off because I'm about out of time.